This is Physics 2211 Lab 1 Constant Velocity by William Barron. So the purpose of this lab is to understand how an object moves when it travels in a straight line at a constant speed. To do this, we will use Tracker to analyze and measure the position over time. Then, using the GlowScript starter code, we will then create a computational model that will predict what the motion will look like. Lastly, we will create a graph of the two and compare them to see the similarities and the differences. Expected results. The results are expected to show that the cart moved at a constant velocity in a straight line, and the position versus time graph from the experiment should form a straight line, and the computational model should closely match this trend, but there is some variation in the two graphs. Now, the fundamental physics principles used in this lab are Newton's first law, which says that an object will keep moving at a constant velocity unless acted on by a net external force, Newton's second law, which is F equals dp over dt, which says since an object was moving at a constant velocity, the net force is zero. We also use V average, which is V equals delta R over delta T. The velocity update formula, which says that V final equals V initial plus F net over M times delta T. And the position update formula, which says the final position equals the initial position plus V average times delta T. Systems and surroundings. For this experiment, the system would be the cart, while the surroundings would be anything else exerting a force onto the cart. For this experiment, the track is the only thing in the surroundings. Observations from the experiment. In the experiment, the observed start time is 0 seconds. The initial position is the origin. The initial velocity is the vector, 0.7575, 0, 0 meters per second, which comes from the formula V equals delta R over delta T. The final time observed is 1.4 seconds, and as you can see, this image on the left shows how the cart has moved along the x-axis in a straight line. Observations from the model. The observations that were gathered from the model were from a computer-generated version of the cart represented by the blue point as it moves away from the yellow point, the origin. Now, it is important to note that the model is a predicted outcome of the experiment and not the actual experiment. Now, plugging in the formulas from earlier, we were able to use the starter code as seen above to model the position and velocity over time as seen on the next slide. Now, as you can see, on the left, the graph shows the position versus time, and on the right, we see the velocity versus time, both in the x direction, from the computational model. Comparing the two. This is a graph comparing the model versus the experiment. The blue line is representing the experiment, and the red line is representing the computational model. Now, both lines show that the position over time was moving, but not necessarily at the same constant velocity, with the experiment having some deviation. Possible sources of error. The possible sources of error when it comes to this lab experiment could be a number of things, such as inaccuracy in placing tracker data points since they had to be placed by hand, slight movement from the camera, and also minor errors in calculations. Now, moving on to some important questions. What if you flip the x-axis? Now, since I chose the right side of the x-axis to be the positive side and the left side to be the negative, it resulted in an upward sloping graph, as seen on the left image, and if I were to flip the x-axis, it would result in a graph sloping downwards, as seen on the right, but this would not affect anything else. What does this mean? Is it possible for you to say how many pushes and pulls, i.e. how many forces, are being added together to give zero net force in the case that you observed? So we know that there are the forces of gravity, friction, and the normal force of the track onto the cart. Now, from our experimental data alone, we cannot say exactly how many other forces were acting, only that their combined effect resulted in a zero net force. So in conclusion, in this lab, we observed and analyzed the motion of a cart rolling across a track at a nearly constant velocity. Using Tracker, we collected position and time data and confirmed that the cart's motion followed a straight line. We then created a computational model based on Newton's second law with the assumption of a net force equal to zero. Now, the model's predictions somewhat match the experimental data, supporting the idea that when forces balance to give a net force of zero, an object maintains constant velocity in a straight line. Now, the slight differences in the experimental and modeled results can be explained by slight imperfections in the setup.